main thing is, so how we can derive the Bernoulli's equation, what is this of the Bernoulli's equations. Okay, so for this condition, so first of all we are going to start the properties of the fluids. So first of all, in general, so we know that fluid mechanics is nothing but we are finding the different types of forces in a fluid when the fluid is in either moving position or in the rest position. Okay. So when coming to the introduction, so first of all, so whenever it comes to the fluid mechanics, so the fluid mechanics is completely depends upon Newton's law of motion. That is Newton's second law of motion. That is force equals to mass into acceleration. Okay. So this is the basic principle. So while coming to the fluid mechanics, so we are having the three laws, so which has been supported for the fluid mechanics. That is law of conservation of mass, law of conservation of momentum, and law of conservation of energy. Okay. So these are the three different laws we are having. Okay. So with the help of law of conservation of mass, so we are finding that continuity equation in one-dimension flow and three-dimension flow. Okay. So while coming to the law of conservation of momentum, we are finding the impulse momentum equation. Okay. And this momentum equation is also used for impact of gas also. Okay. And the next thing is we are having law of conservation of energy. Okay. So the law of conservation of energy, so we are finding the Bernoulli's equations. Okay. So with the help of these three different formulas, so we are getting one equations. Okay. So at the same time, so including these three, we are having the major formula force equals to mass into acceleration. Okay. So complete on this flow, so the fluid mechanics is dependence. Okay. So first of all, so when coming here, we are having so three case studies in the fluid mechanics. Okay. That is, so first of all, we need to know that. So what are those three case studies? Okay, that is fluid statics, fluid kinematics, and fluid dynamics. Okay. So here we are finding that the fluid mechanics is nothing but, so it is a branch of a general sciences. Okay. So which will deal with the behavior of the fluids. Okay. So while coming to here, so we are having that for which type of fluid, so which property. So we are having different types of names for the fluids. Okay, those different types of names and those different types of characteristics comes from the properties of the fluid. Okay, so by seeing one fluid, so we can aim to conclude that, so okay, the name of the fluid is so and so. Okay, and the fluid belongs to so and so type of fluids, like this. Okay, so first of all, we need to know that we are having the different types of properties of the fluids. Okay, so first of all, here we are having the fluid statics, fluid kinematics, and fluid dynamics. Okay, so coming to the fluid statics, so in fluid statics, we are finding the forces of the fluid. So the fluid is in first position. Okay. So right now, we are going to discuss about, so what is the fluid static. Okay, that means here itself, so we are finding the different types of the force. The fluid is in the rest position. That means the object should be in the rest position. Okay, so here we doesn't consider any types of forces. Okay, so we are considering only the nominal forces. Okay, so while coming to the fluid kinematics, so here we are finding the forces when the fluid object is in the motion, okay, but without considering of the external forces. Okay, so ఇక్కడ మీరు క్లియర్గా అబ్జర్వ్ చేసినట్లయితే, so we are having that, so two types of forces. Okay, that is, so we are taking the fluid in the rest position, fluid in the moving position. Okay, so right now, so we are telling about the moving position. That means the fluid should be moved from rest positions to moving position, 0 to velocity. That means we need to apply a little bit pressure. Okay, so the body is in the rest position. Afterwards, we can apply some pressure. Then only the body will move to 0 to some extent. Okay, or otherwise, if the surface of the body is in inclined position. Okay, so the fluid is placed on the top position, so automatically the surface will be in inclined position, that is top to bottom. Then without considering any forces, without considering any external forces, so the fluid is moving from top positions to bottom positions. Okay, so these are the two methods to find out the moving part of a fluid. Okay, that is we are finding the forces that is fluid statics and fluid kinetics and fluid dynamics. Okay, so as coming here, so we are having different types of fluids. Okay, so based on the types of fluids, okay, so some different properties are also there. Okay, we are having so four types of fluids are there. Okay, first thing is ideal fluid, real fluid, so Newtonian fluid, and non-Newtonian fluids. Okay, so see here. Yeah, so these are the types of fluids we are having. So please see here carefully. So we are having ideas. Okay, so what is meant by ideal fluid? So what is meant by real fluid? What is meant by Newtonian fluid? What is meant by non-Newtonian fluids? So okay, so because number of fluids, okay, so any one of these types, that is either it should be ideal or it should be real or it should be Newtonian or it should be non-Newtonian. Okay, so if you go for the ideal fluid, okay, ideal fluid is a fluid which is incompressible and it doesn't have any viscosity. Okay, which is known as the ideal fluid. Okay, so those ideal fluids are also known as imaginary fluids. Okay, so the best example for ideal fluid is water. Okay, so ideal fluid is nothing but ideal fluids are incompressible fluid and doesn't have any viscosity. That is zero viscosity. Okay, so that is negligible viscosity is there. Okay, so I'll come into the real fluids. Okay, so a real fluid have some viscosity. Okay, so it should be used in the regular practices. Okay, it should be used for regular practice. Okay, so I'll come into the Newtonian fluids. So here we are having, so we need to consider that the velocity gradient. Okay, so while coming to here, so we are having the real proportional to the shear strain. Okay, it's known as Newtonian fluids. Okay, so while coming to here, Newtonian fluids. So Newtonian fluids are real fluids where the shear stress is directly proportional to the shear strain. Okay, so while coming to the non-Newtonian fluids, so non-Newtonian fluids is also a real fluids in which where the shear stress is not proportional to the shear strain. Okay, so these are the four important types of fluids. So again, I'm repeating that we are having four different types of fluids. Those are ideal fluids, real fluids, Newtonian fluids, and non-Newtonian fluids. Okay, so while coming to the ideal fluid, so the fluid has incompressible and it doesn't have any viscosity. So while coming to the real fluids, so real fluids have some amount of viscosity. Okay, and which should be used in the regular purposes or the regular practices. So while coming to the Newtonian fluids, the Newtonian fluids are real fluids. Okay, where if the shear stress is directly proportional to shear strain, then the fluid is known as the Newtonian fluids. Where the shear stress is not proportional to the shear strain, then it is known as non-Newtonian fluids. Okay, so listen carefully. So depends upon these types of fluids, we are having different types of properties, and the property should be vary from each liquid. Okay, that is we are having water, diesel, kerosene, greases, oils, okay, petrol, okay, some applications, okay, then mercury, like this we have different types of fluids. Okay, so position and the viscosity at the same time. So the moment of the fluid flow, okay, will define that either the fluid comes to a ideal fluid or real fluid, or Newtonian or non-Newtonian fluids. Okay. See here. So basically, we are having different types of properties. Okay. So those properties are mass density, specific weight. So mass density or density. Okay. Specific weight or weight density, specific volume, specific gravity, surface tension, vapor pressure, compressibility, capillarity, viscosity, cohesive forces, and adhesive forces, and vapor pressure. So like this, we are having number of properties. Okay. So again, I am repeating the properties. So please note down. So density or mass density, specific weight or weight density, specific volume, specific gravity, cohesive forces, adhesive forces, surface tension, viscosity, capillarity, vapor pressure, so bulk modulus, compressible, like this. The number of fluids are like this number of properties of the fluids are there. Okay. In the same way, so we are having different types of flows are there. Okay. So for fluids, we have different types of flows. So those are uniform flow, non-uniform flow, steady flow, unsteady flow, rotational flow, irrotational flow, laminar flow, turbulent flow, one dimension, two dimension, three dimension flows. So these are the different types of flows are there. Okay. So based on these different types of flows, so the flows are forming the different types of flow patterns. Okay. So we are having four types of flow patterns are there. Okay, we are having four types of flow patterns are there. So those are, the first thing is the streamline, streak line, path line, and the stream tube. So these are the four flow patterns for the fluids. Okay. So see here. So while coming here, so first of all, so we are going to find out that mass density or density. Okay. So here, so density is defined as, or the density is the ratio of mass of the fluid to its volume of the fluid. Okay. So mass of the fluid to its volume of the fluids. So mass is nothing but kg and volume is nothing but meter cube, and the units for density is kg per meter cube, and it is denoted by rho. Okay, that is rho equals to the mass by volume. So rho equals to mass by volume, and the units are kg per meter cube, and the units are kg per meter cube. Okay. So next one. So weight density. Okay. So weight density is nothing but it is the ratio of weight of the fluid to its volume of the fluid. Okay. Again, I am repeating that. So weight density is nothing but, here we are having that. So W equals to, that is, so it is the ratio of weight of the fluid to its volume of the fluids, and it is denoted by W. So W equals to weight of fluid divided by volume of the fluid. Okay. So weight is nothing but, mass into acceleration due to gravity. That is, weight of the fluid is nothing but mass of the fluid into acceleration due to gravity of the fluid. Then volume of the fluid is also there. Okay. So mass of the fluid is nothing but m. So an acceleration due to gravity is nothing but g, and volume of the fluid is nothing but v. Okay. So here we are having m by v is nothing but rho. Okay. So mass by volume into g. So mass by volume into g. Here we can find that mass by volume equals to rho. That's m by v equals to rho. So while coming here, we are having mass of the fluid divided by volume of the fluid into g. That is m by v into g, which is nothing but rho into. Therefore, W equals to rho g. Okay. So and here also we are having the units is same, that is kg per meter cube. Okay. Then specific volume. Okay. So specific volume is nothing but it is the ratio of volume of the fluid to its mass of the fluid. So volume of the fluid to its mass of the fluid, that is so V by M. Okay. If we see the mass density, we are having M by V. So if we go for the specific volume, we are having V by M. That is, the specific volume is equals to the reciprocal for mass density. That is, specific volume equals to 1 by rho. Okay. So and it's commonly applied to any type of gases. Okay. And the units is meter cube per kg. Okay. So while coming here, we are having the specific gravity. So specific gravity is very important. Okay. So with the help of the specific gravity, so we can find out the thickness and the viscosity of the fluids, and the regular formula or the regular procedure for the specific gravity is, so we are having different types of specific gravities for each liquid. Okay, for water we are having 1, for oils we are having 0.7, okay, 0.7 to 0.9. So for kerosene petrol we are having 0.786, okay, for mercury we are having 13.6. So here for specific gravity, we doesn't have any units, okay, or we doesn't have no units, okay. So why? Because so the basic formula for specific gravity is, it is the ratio of weight density of the liquid, to the weight density of the standard liquid, okay. So weight density of the given liquid divided by weight density of the standard liquid, okay. So we are having weight density in the numerator and denominators, okay. If both get cancelled, means automatically it will comes for the unit quantity. So due to this condition, we don't have any units for specific gravity, okay. That means so we doesn't have any units, 0 units for specific gravity, okay. So for example, if we want to take the specific gravity for liquids, so we need to find out the weight density of liquid, that is weight density of the given liquid divided by weight density of the standard liquid. Standard liquid is water and the given liquid is whatever they have given. So we need to take that. For example, so if they has given that mercury as a liquid, means so the weight density of the liquid is, so weight density of mercury is 13.6 into 1000. Okay. For water we are having 1 into 1000. Okay. That is 13.6 divided, so 13.6 into 1000 divided by 1 into 1000. Okay. So then we will get that 1000 will be cancelled. 13.6 divided by 1 equals to 13.6. Okay. So like this. So please see this. So this is the different types of the specific gravities as allotted for the different types of fluids. Okay. So here we are having the different types of substances. Okay. For example, water we are having 1. For blood we are having 1.05. For seawater we are having 1.025. For gasolines we are having 0.7. For ethyl alcohol we are having 0.79. For mercury we are having 13.6. For wood we are having 0.3 to 0.9. For gold we are having 19.2. For bones we are having 1.7, and it ranges from 1.7 to 2. For ice we are having 0.92. For air, for 1 atmosphere we are having 0.0013. Okay, these are all the specific gravities for this one. These are the standard specific gravities. Okay, so based on the fluid mechanics, so we are getting minimum 3 to 4 bits per gate. Okay, so while coming to the first bit, so they will ask on any property, and they will ask the pressure measurement devices, which is nothing but the manometers. Okay, so I will show that also. Okay, yeah, and the most important property of the fluid is viscosity. Okay, so viscosity is nothing but it is a property of the fluid, so which offers the resistance of the movement of layer by layer to the adjacent layer. Okay, so the basic formula is nothing but, so viscosity is nothing but to resist the fluid when it is in the moving positions. Okay, so it needs to oppose the fluid, and it needs to resist the flow of a fluid. Okay, so viscosity is nothing but, so viscosity is defined as a fluid which has so which offer the resistance to the movement of one layer of fluid over the another adjacent layer of the fluid. Okay, so when we take any surfaces, so we'll pour some water on that. Okay, so whatever the pressure we has given at starting, so I'll come into the ending position, it will be zero. Okay, because the surface has the capability to resist the flow of the flow. Okay, to resist the flow of the fluid. Okay, so instead of water, if we pour any oil means, so it has a different specific gravity and it has a different viscosity. Okay, so like this. So the general formula for viscosity is tau equals to mu into du by dy. Okay, so here we are having this one. Okay, so this is starting point. So if we assume this is a water or this is a water surfaces, okay, if we apply any negligible pressure, okay, so our negligible, so force on a fluid, so with the help of some wind, so with the help of some wind, the water is moving from one place to another place. But so for every lake or pond or water, it may be a river, so we are having so one open surface and down surfaces. Okay, so that height will be divided into number of parts. Okay, whenever some air will be passed on the atmosphere, so atmosphere on the level of the water on the first surfaces, so automatically the layer will be moved. Okay, so when that layer will be moved means, so automatically we are having another adjacent layer and it will be resisted to stop the flow. Okay, so here we are having that tau equals to mu into du. So tau equals to mu into du by dy. While coming to mu, we are having the viscosity, and du and dy is nothing but so change of velocity with respect to the change of the distance. Okay. So like this we can, yeah, listen. So see the formula here. So mathematically it will be explained that tau equals to mu into du by dy. Okay, and we need to find out that mu equals to so tau divided by so du by dy. Okay, and the units of viscosity is newtons. So newton second per meter square, because the mu equals to shear stress divided by that's tau. Tau is nothing but the shear stress, and du is nothing but change of velocity, and dy is nothing but change of the distance. So we'll come into here, shear stress equals force by area. Okay, so while coming to the viscosity, so units of viscosity we are having newton seconds per meter square. In the same way, we are having that kinematic viscosity, that is mu by rho. Okay, so kinematic viscosity is nothing but mu by. Okay, so and we need to find out that Newton's law of viscosity. So Newton's law of viscosity is nothing but it states that the shear stress on a fluid element layer is directly proportional to the rate of the shear strain. Okay, so here we have in the constant proportionality. The constant proportionality is nothing but the coefficient of the viscosity. Okay, so listen. So the viscosity of a fluid is completely depends upon the temperature of the fluid. Okay, so generally when the temperature increases, automatically the viscosity will be decreases. If temperature decreases, the viscosity will be increases. Okay, so the better example we can take as, so either we will go for different types of oils or different types of so ice cubes, whatever it may be. Because so for example we are taking the water, okay, as a first phase, okay, and we are so going to keep in so 0 degree centigrade. Okay, automatically so we are so cooling down the temperature, that means we are reducing the temperature. Okay, then so well in the water we are having the so loose molecules are there. Okay, so whenever so we are reducing the temperature, okay, at that time so those molecular bonds come closer and it will become the solid. Okay, and viscosity is more. Okay, so like this, but otherwise So if you take any oil or any ghee or whatever it may be, or any butter like this, okay, so it will be in sticky nature. Whenever the temperature increases, automatically the viscosity will be decreases. Okay. Yeah. So see here. Another important property is compressibility and bulk modulus. Okay. So I'll come into the compressibility. So whenever you are applying the pressure on sides, then automatically, so we're having the deformations and so changes in the object. Okay. So compressibility is nothing but it is reciprocal of bulk modulus with the elasticity. Okay. So here compressive strain. So we are having that. So it is defined as the ratio strain. Okay. So while coming here, we have that bulk modulus K equals to increase of pressure divided by so volumetric strain, and compressibility equals to 1 by K. So these formulas are very important to do the problems. Okay. Another property is surface tension. Okay. So surface tension is nothing but it is a property of a liquid surfaces. Okay. And so how much it has been extended the pressure and it will came to the surface tensions. So while coming here, surface tension, we are finding the surface tension on a liquid droplet and a soap bubble at the same time. So cylindrical jet. Okay. So if we need to find out the surface tension means, so here we need to go for, so when you take any one of the droplet and it should be divided in the two sections. Okay. So while coming to one section, so pressure will be added and another section surface tension will be added. So on these two conditions, okay, so we are having circumference and the cross section area. Okay, that is pressure on the surface. So pressure on the surface is equals to the surface tension on the circumference. Okay, that means it should be like this. Okay, so here we have two types of forces. That is pressure forces and surface tension forces will be terms. Okay, so while coming to here, so we are having so tension forces and the pressure forces. Okay, then so surface tension forces is nothing but so it acts on the circumference. That is the sigma into circumference. Okay, the circumference formula is 2 pi r or pi d. Okay, so I'll come into the pressure forces. So we are having P into A. So pressure forces. So forces equals to pressure into area. Okay. Then here we are having P into A. Then A equals to pi d square by 4. So while conclusion, so while we conclude that first equation equals the second equation, so we will get so 4 sigma, that is sigma into pi d equals to so P into pi d square by 4. Okay, P into pi d square by 4. And we will get the formula that P equals to 4 sigma by D. Okay, because here pi d will be cancelled and only D will be there. That is P into D. At the same time, here we are having 4 sigma. Okay, that is P equals to 4 sigma by D. So surface tension of liquid droplet equals to so 4 sigma by D, and the meter square. So I'll come into the halo bubble. So halo bubble means, so here we have another, so two diameters will be there, that is internal diameter and external diameter. So while coming to the liquid, so we have on internal external diameter. Okay, and the present surface tension acts on same conditions. So while coming to here, we are having the pressure forces and surface tension forces. That is P into A equals to sigma into. So here we are having two perimeters, I mean two circles, that is two diameters. So that's why here we are having so 2 pi d. Okay, while coming to the liquid droplet, we are having only one circumference and we'll take that so pi into d. Okay, here we are having 2 pi into d. Okay, equals to so P into pi d square by 4. 8 sigma by d. Okay, P equals to 8 sigma by d. In the same way, here also we have for liquid cylindrical jet also. That is P equals to 2 sigma by d. Okay, so these are the three different types of formulas we are having for surface tension. That is surface tension for halo bubble 4 sigma by d, and 8 sigma by d, So while coming to the surface tension for liquid droplet, we have 4 sigma by d, and surface tension for hollow bubble is 8 sigma by d, and the surface tension for liquid cylindrical jet is 2 sigma by d. Okay, so these are the important factors, and the units are Newton per meter square. Okay, so and here we are having different types of vapor pressures are there. Okay, so we are having so 4 different types of vapor pressures. Okay, those are atmospheric pressure, absolute pressure, so gas pressure, and the vacuum pressure. Okay, so if we find out any pressure, or if we find out any pressure value, it is nothing but gas pressure. Okay, so what are the pressure we are finding? Okay, so it's nothing but the gas pressure. Okay, if any pressure, so we are having in negatives, so it is nothing but the vacuum pressure. Okay, so first of all, we need to know that what is my absolute pressure. So absolute pressure is nothing but it is defined, which is measured with reference of the absolute vacuum pressure. Okay, so gauge pressure is nothing but, so it is the pressure which measured with the help of any pressure measuring instruments. Okay, so here we have that pressure measuring instruments. Okay, so I'll come into this. So we are having so 2 different types of pressure measurement devices are there. Okay, so those are, the first thing is mechanical gauges, and the second thing is manometers. So first thing is mechanical gauge, and second thing is manometers. Okay, so I'll come into the manometers. So manometers are the devices which is used to find out the pressure. Okay, so while coming to this type of manometers, we are having the simple manometers and a differential manometers. Okay, again the simple manometers is also classified into so 2 or more sectors, that is piezometer, U-tube manometer. Okay, and differential manometers having that U-tube differential manometer and inverted U-tube differential manometers. Okay, so like this we are having the manometers. Okay, so see here, and afterwards we are having the capillarity. Okay, if we introduce the capillary tube in any beaker, okay, so if we are having some water on the beaker, if we put some pressure and if we apply, okay, then while coming to the capillary tube, so the surface level will be here and the water difference level will be there. So while coming to the beaker water level and capillary water level, so the capillary water level is more than the vessel water level, then it's automatically known as capillary rise. Okay, or otherwise here we are having the capillary water level. So if the water in the capillary tube is less than the regular level, means it is known as capillary depression. Okay, so on the formula is H equals to 4 sigma cos theta by rho GD. So H equals to 4 sigma cos theta by rho GD. So theta equals to 0 degrees for water and theta equals to 130 degrees for mercury. Okay, so we can use any type of fluid. For one type of fluid we are having different types of angle. So basically we are having 2 fluids, that is water and we will take mercury. So for water it is 0 degrees and for mercury it is 130 degrees. Okay, so the exact angle is 128 degrees. Okay, and the formula is H equals to 4 sigma by rho GD. If the H value comes in negative means it is capillary depression. If the H value is in positive means it is capillary rise. Okay, see here, it should be like this. Okay, yeah, so these are the measurements of pressure we are having. Okay, so manometers are the measuring devices for the pressure. Okay, so here we are having the manometers, and the manometers are classified into 2 types, that is simple manometers and differential manometers. Okay, so while coming to here we are having the simple manometers and the differential manometers. Okay, so while coming to simple manometers we are having the piezometer, U-tube manometer and single column manometer. So while coming to the differential manometer we have U-tube differential manometer and inverted U-tube differential manometers. Okay, the regular formula for the pressure we need to find out means rho into G into H. So rho into G into H. So I'll come into the simple manometer. We are finding the pressure only So one area, and we have low pressure. Okay. So we'll come into the differential manometers. So there we are having. So we are finding the differences of the pressure between any 2 points. Okay, any 2 points. Okay. So I'll come into the simple manometer. So one end of the manometer is opened into the atmosphere. Okay. So I'll come into the differential manometers. Here both will be doesn't have the atmospheric pressure value. Okay, it should be like this. And the formula for so here is for piezometers P equals rho GH. For E2 manometers, so P equals rho GH1 minus rho GH2. So I'll to differential manometers. So name itself indicate differences. Okay, differential differences. That is we are finding pressure differences between 2 points. That is P1 and P2. Okay, so it should be like this. Okay, so see here. So one end will be open into the atmosphere. Okay, so I'll come to differential manometers. So both are closed ends. Okay, so here we are finding that the differences in the pressure in the point A and point B. Okay, like this. Okay, so based on this one, we are having some gate problems also. So that is see here. So this is a an inverted pipes can be as shown in the figure. Okay, so pipe A is carrying oil. Okay, that's pipe A is carrying oil with a specific of 0.8, and pipe B is carrying water. Okay, pipe B is carrying water. Okay, so the densities of air and water is 1.16 kg per meter cube. Okay, the densities of air and water is 1.16 kg per meter cube and 1000 kg per meter cube. Okay, so the pressure differences between the pipe A and B is so dash below Pascal. Okay, so here, so see here. So first of all, here we have PA minus rho GH. Okay, if it is normal manometer means PA plus rho GH we can take, but right now we need to take that. So PA minus. So A minus so 1 equals. So first of all, we are splitting this one. So that is L equals plus. Okay, we have PA minus PB minus rho GH2 plus rho GH3 because here we are having 3. Okay, so we are having that. So two different types of fluids are there. Okay, and they has given the specific gravity also, that is 0.8. Okay, so first of all, so P minus rho GH1 minus rho GH2 equals to PB minus rho GH1. Okay, that is so PA minus PB equals to rho of oil, that is 0.8 into 1000. What a mass density here, then. Okay, so for mass density we are having a specific gravity into weight density. Specific gravity is 0.8 and weight density is nothing but 1000. Okay, and the height is 10, and so here we are having 0.2 as H2. Okay, and H1, and D is nothing but 9.81, and they have taken the round figure as 10. Okay, so like this we are substituting this one, that is so density of oil, gravitational force, and H1 minus so density of air, gravitational force H2 equals to so density of water. Okay, so like this. So like this we are substituting this one. Okay, so and here we will get the answer that PA minus PB equals to minus 2.199 kilopascal. So here we are having that minus, which is nothing but here the pressure is vacuum pressure. Okay, so see here. So while coming to another one, here we are having so oil of so here we are having the oil which 10 meters per second. Okay, and the water is flowing through a okay. So what we need to find out the so velocity of water, we need to the similar equal to 10 to the power 5 this is the model. So while coming to the prototype, so I Okay. So while coming to water, we need to find out. Okay. So here we have this. So 1 into 10 to the power of minus 5 and the diameter is 0.5 meters. So coming we are having diameter equals, that is, and the diameter is 800 into the power of minus 4 meters square per. Okay. So right now, so our formula is prototype equals to model. Okay. That is, here we have that model of oil equals model of water, which is nothing but Reynolds number. So Reynolds number of oil equals to Reynolds number of water. Okay, which is nothing but velocity into diameter viscosity of prototype. Okay. So this minus, well, coming to the velocity 10 and the diameter 0.5 meters. And here we are having, so kinematic viscous gas 1 into 10 to the power of minus 5. Okay, out of this 1, 2, 3, 4, 5, 6 terms, so we are having only one unknown term, that is V equals to. Okay, so right now we can find out that VW. Okay, that is velocity of water equals to 22.25 meter per second. So like this. Okay, for example, if we need to find out the Reynolds number, so we are having different types of formulas. Okay, so for example, if we need to get the Reynolds number, so first of all we need to find out the inertial forces divided by viscous forces. Okay, so first of all, the basic formula of Reynolds number is comes from, so inertial forces divided by viscous forces. That is, so the basic formula we are telling that force equals mass into acceleration is nothing but, so force equals to mass into acceleration. That is F equals m into a. F is nothing but summation of all forces equals to mass into acceleration. Okay, that is either it should be gravitational forces or pressure forces or weight forces. Okay, or thermal forces or temperature forces, whatever it may be. So forces equals to mass into acceleration. Okay, summation of all forces equals to mass into acceleration. That is, so Fp, that is pressure forces. Fg, that is the gravitational forces. Inertial forces, viscous forces, like this. Okay, if we are reducing one, so one type of so if we are neglecting one forces, okay, or if we are removing one type of forces, then we will get one type of equations. Okay, so with the help of weight forces and pressure forces, we will get the Euler's equation. Okay, with the help of inertial forces and with the help of viscous forces, so we will get the Reynolds number. Okay, so with the help of, so gravitational forces and inertial forces, we will get the Froude numbers. So like this, so we are getting the number of forces. Okay, if we need to get this one means, so we need to solve that. So inertial forces divided by viscous forces equals Reynolds number, and the Reynolds number, so regular formula is, so that means we need to find out, so this Reynolds number will be used in, so to find out the friction resistance, that is F dash equals to 0.079 divided by, so Re whole power 1 by 4. Okay, so at the same time, with the help of Reynolds number, we can conclude that either the flow is either laminar, turbulent, or transition. Okay, so we came to conclude that, so if the Reynolds number is less than 2000, if the Reynolds number is less than 2000, the flow in the pipe is laminar. If the Reynolds number is more than 4000, the flow is turbulent. If the Reynolds number is more in between 2000 to 4000, then the flow is transition. Okay, so like this we are having different types. Okay, so most probably, so in every gate exam, so the fluid mechanics having, so it's 3 to 4 bits. Okay, so we'll come into the tomorrow classes. Okay, so I will discuss about, so what are the, so previous, so bits they are asked. Okay, so like this. Okay, so see here, so a steady laminar boundary layer is formed over a flat plate as shown in the figure. So the free stream velocity of the liquid is, so u naught, The velocity profile of the at the inlet of A and B is uniform, while that the downstream location CD is given by, okay, like this. Okay, and we need to find out the answers. Okay, they have given u equals u naught into 2 of y by delta minus y by delta whole square. Okay, so we need to find out like this. Okay, and here we have a steady state process that, so integral of rho equals rho of dA equals to 0, and the cross section transfer we have in the surfaces. So I'll come to here. So we are exploiting that one. Okay, and we'll get the final answer. Okay, so minimum of 3 bits will come. Okay, so minimum of 3 and maximum of 4 will come in fluid mechanics. Okay, so here I'll come to the tomorrow classes. So we'll discuss about, so what are the previous problems they asked and how to solve that. Okay, and so I'll come in here. So, and again we need to go with the important topics of some manometers, and afterwards we'll discuss about, so steady flow, unsteady flow, uniform flow, non-uniform flow, rotational, irrotational, compressible, incompressible, laminar, turbulent, one dimension, two dimension, three dimension, and continuity equation and its uses. Okay, Euler's equation and its uses. Okay, then Bernoulli's equations and its uses. Okay, so these are most important topics. Okay, so based on these topics only, so we'll get the bits. Okay, సో ఇంకా హైడ్రాలిక్ మిషన్స్ పైన, సో వాటిపైన సో అడగరు. సో ఇప్పటివరకు మనం ఏదైతే చెప్తున్నామో, సో ఈ ఓవరాల్ ఈ ప్రాపర్టీస్ పైన మనకు బిట్స్ ఎక్కువ వస్తూ ఉంటాయి. ఓకే, ఇఫ్ యూ హ్యావ్ ఎనీ డౌట్స్ యూ కెన్ ఆస్క్. Anybody is there? Anybody is there?
Sir, no doubt, sir.
Yeah, okay. Vamsi sir? Vamsi sir?